I will also send you a link to the other one, but that is just to look for your knowledge because kind of structure is important, especially protein structure. But I will the part that's going to be on the exam, I will associated with protein structure. I will actually give you a I will give you a demonstration of that because even beyond the exam, I think you need to understand some of that. Okay. So let us begin. Today's lecture is I call it Introduction to Biostatistics, but it's really an introduction to statistics. And okay, before I continue, does anybody have any questions related to the final exam? Okay, so the final exam again, if this was, if it's a question that's been kind of going in your mind and it's not something you can articulate. The exam will be on everything and anything, okay? But to be able to succeed in the exam, no memorization will be required. You will not require to memorize anything. Everything that you would need, everything that you would need in terms of knowledge, in terms of kind of remembering anything, will be provided directly to you. You will have no reason to memorize anything, okay? If a formula is required, it'll be given to you. Applying the formula. So if you, as you study for this exam, as you go through your notes, what I'm expecting is the material that we've gone through, and understanding of it is important. There will also be a homework that will be due on exam time. Okay. But again, like I said, I apologize because I didn't realize that I was going to be one class short. But at the same time, it's kind of balancing out, just staying within the time limit of the exam, and also the kind of balancing out not being able to give you one bit of instruction. So that instruction, the link to the video will be yours to use as you see fit. The only issue is, that's what there'll be a homework due, and once again I apologize, but a little bit of hard work would be is worthy of your is worth your time. Okay. Alternatively, if you want to take the exam on the 8th, as opposed to actually one of the things that we can do is we can have the class. I'm Oh no, never mind, sorry. Yeah, it's the week of the 7th and the 8th. So I'll tell you what I'll do. We will have next week's class. Okay, we will have next week's class, but more as a perfunctory, and the exam will be on the 7th or the 8th. So right now in your chat, and it'll be like between 1 and 3. Now, as uh, alternatively, again, so why don't you tell me whether it's the dates of the 7th or 8th, which one is preferable to you? uh, to have the exam, like date and time. So basically, we are do talk. It's going to be a 3-hour exam, so it's going to be morning or afternoon, or the 7th or the 8th. I kind of I was right on my scheduling time. I thought we were a class short because for some reason I thought I thought 7th and 8th was actually was Monday, but it turns out it's not. So, all right, I need some answers now. Text message, text. I've got the chat open, so you can tell me which one's a better time for the final exam. All right, and then we'll come to a mutually agreed time. And then if you can't be there, then we'll make some alternate arrangements. How about let's go from Thursday? All right, so let's get okay. So Michaela, Yuchia, Win, Maylene, Ayman, tell me. Okay, you have. Oh yes, that's correct. You have a class on Thursday. Friday is good for you. Thursday is good for you. Friday is good for you. Okay, I'm good either day, man. Thank you. Okay, Yuchia, can you tell me what your preference is? you prefer before Thursday. Okay, so are we in agreement now that each of us is going to take the exam on any day we want? The only reason Yuchi is the only one who's now throwing a spanner in the works, but that's okay. The only thing is, I want to make sure that that if we have for everybody, then the issue is proctoring the exam, right? Proctoring the exam, because somebody's got to sit there and watch you guys for 3 hours, and um, like again, my daughter's generally with me at work, so I could potentially dump her. Actually, I could potentially dump her. And Yuchia, would you prefer to take the class in my office on a Wednesday afternoon, for example? Okay, so Friday is also good. Okay, so we can do two things. So we have, how about Friday 10 to 1 for Maylene, Eman, Yuchia, and Nguyen. Michaela likes afternoons because I have field work in the morning. Maylene will be on campus all day Friday. Okay, all right. Can we decide then 2 to 5 on Friday? I think this will be good for everybody. Okay, I think that's a good time, 2 to 5 on Friday. Michaela, you'll get a chance to come back from your field work, put your feet up, and I'll try and book room number 120 and the experimental sciences building, and this way, I can be sure that, because it looks like Friday is a good time for everybody, and I'll have your grades in by Monday. I'll probably grade it really quickly. Okay. All right. Are we all agreed on that? And I will confirm. Okay. So final exam 2 p.m. to 5 p.m. on Friday. Location ESB 120. Okay. I think that would be great. And again, if there are any issues related to the if there are any issues related to the location, I'll find another place for you. Okay. All right. Thank you. We are agreed. Thank you for being accommodating, and sorry for the confusion. Sorry for all the confusion. Okay. Let us now begin. And so, again, if we went to the introduction to biostatistics, it's not really an introduction to biostatistics, it's more of a teaser. Uh, and while it's a teaser, let me find out. Um, So the reason it's a teaser is not, I'm not saying that you should necessarily take this course, but if, biostatistics seems to be getting more and more popular, uh, now. But let me just find out the course number. Those of you who are interested, um, the biostatistics in nutrition. Now, this is not necessarily biostatistics in nutrition so much as that you will learn biostatistics. You learn how to program in R. It's a course that's being taught in spring, and it's in the nutritional sciences, and NS is nutritional sciences. And as a teaser, I teach BTech 5333, which is advanced bioinformatics, uh, where also in spring, in case you guys are interested. Not saying that you should, just throwing it out there. And one of the things that we can so in that class, and again, because while I have you here, and again, you can, if you think about it but then forget the course number and things like that, you can always let me know. So it's advanced bioinformatics. You will learn how to program in Python, and no prior programming experience is necessary. We start right from the beginning. You will also write, you know, then you will learn so now this is not a Python programming language so much as it's a Python programming language just so you can learn BioPython, where a lot of the things that we have learned this semester, we can actually write programs to do it ourselves. Okay, a lot of the things that you've seen on the web and things like that. Okay, so again, if you are so inclined, you can ask. Okay, biostatistics, as I think it's taught by a professor, Surya Niraula, at Nutritional Sciences Center, and Advanced Bioinformatics is something I will teach. In addition to the Python, BioPython part of the program course, you will also learn the second part of the class is programming, is how to create protein models. So it's protein modeling and protein ligand docking or protein ligand interactions. Okay, so those are the two things that in my class, and biostatistics is kind of getting more and more, becoming more and more prominent. Okay, again, the chat is open. I'll see the little notification as the little red light shows up over the chat button in Teams, and we'll go from there. Okay, all right. If there are no other questions, just to reiterate. Uh, I'm teaching this class in spring, Advanced Bioinformatics 5333. Again, it's a great course if you want to learn, if you want to kind of develop your programming skills, especially in the bio area. You will also be able to, again, nutritional sciences class. So in nutritional sciences, you're not just going to learn the fundamentals of biostatistics, some of which we will touch upon now, but you will also learn uh, programming in R, the fundamentals of programming in R, and then there, just like the Python, and then the bio aspect of Python is BioPython. The bio side of R is bioconductor, and a lot of developments to make things easier in biostatistics are in place. A lot of the analysis basically is also being done in R. It's a great skill to have if that's a direction you want to take your education and learning in. Okay. Okay, let's begin biostatistics, and it's really not really about biostatistics. It's just I think it's a good place to kind of learn a little bit of statistics, just to get that foundation. So if you wanted to launch into biostatistics, that's something you could do. All right, now we're going back to the definition of what is bioinformatics. And the reason we're going back into this definition is because you'll see some interesting parallels between that struggle we had in terms of in bioinformatics was how does one have a kind of all-encompassing definition without making it too long and too verbose, right? How do we have an all-encompassing definition which is relatively speaking succinct? So in biostatistics, you have the same problem. So again, remember, biology is always is should always be an experimental science. Any kind of any kind of discovery-based bioinformatics, if you do, because most of my personal research is discovery-based bioinformatics, it falls into the realm of what is called hypothesis development. So you develop a hypothesis, you potentially test it. Again, remember we are talking about the scientific method here. So you develop a bio you develop a hypothesis, you set it into a thesis, you test the hypothesis. If the hypothesis comes true, then you also kind of try in another setting to replicate the results just to ascertain. If not, then you go back to the hypothesis drawing board and then come up with another hypothesis. Okay, and that's the foundation. That is the foundation of the scientific method, which people tend to forget. Okay, so it should be experimental science. Bioinformatics is designed, in addition to some of the other stuff, is designed to be something that will support, that will provide a computational, very often a mechanistic basis for what it experiments is a black box, right? So I'll give you one example. Let's say you mix two compounds. For example, you mix sodium sulfate, which is a colorless liquid because sodium sulfate is soluble in water, and then you mix it with barium sulfate, which I think is also colorless, or sodium carbonate and barium sulfate, both of which are colorless. But the moment you mix them together, it instantly produces a milky precipitate, which is barium carbonate, right? That's what's called it's basically in high school you learned as what's called the double decomposition reaction. So that is instant, right? So, but on the other hand, if you actually were able to slow down that reaction to levels of 10 to the negative some seconds, and you could take each of those snapshots, you will probably see that while the reaction seems instantaneous to you, you will probably see that you have many side reactions that take place. And if you could kind of have these pulsed lasers as femtoseconds, you'll probably see all these intermediate products being created, like weird complexes before it goes into the direction of creation of a barium carbonate, which is a precipitate, right? And I might have my chemicals wrong, but I think the point is still the same. Uh, so so what happens is that when you pulse that femtosecond, which is 10 to the negative 15-second laser, you get these millions of snapshot, billion, actually multi-billion snapshots within a space, which, and a femtosecond is a trillionth of a second, right? 10 to the negative 15. So you get to see um, a trillion snapshots. So you see what kind of intermediate reactions take place before the final product is created. So on the other hand, if you just were in a lab and you just took those two colorless liquids and you ran a double decomposition reaction, you would only be able to say, oh, this is what I started with, this is what I got, here are my observations, right? But what bioinformatics, and to use that analogy, is something that allows you a mechanistic glimpse into what is potentially happening. Okay. And this despite the fact that that without, obviously, bioinformatics is not possible without computational infrastructure. Okay, so you need the biosciences in order to make sure that a that a field of study like bioinformatics exists. All right, so now what we're going to do is draw parallels between bioinformatics and biostatistics, and you will see that there is the exact same struggle of trying to define biostatistics. All right, so let's go to Vanderbilt's and see. Biostatistics is a branch of statistics responsible for the proper interpretation of scientific data generated in biology, public health, and other health sciences. Okay, so one was the kind of the things about sequences and things like that. Now you have basically the statistical application to, okay, it was information technology application in the biosciences. Now it's information technology in the area of statistics, or statistical applications in the realm of biology. Now, when we talked about statistical things, we also at some point when we did our high throughput genomic level work, we looked at microarrays, and at that time I made the point that microarrays actually gave rise to biostatistics, because when you look at an ensemble determination, it's very difficult to just use simple then you got to consider too many factors, and when you put too many of those factors, when too many of those factors are involved, then you have to have statistics. And remember, I said the first papers in microarrays were so popular that people just blindly went and published something, and then they could not be replicated, and all kinds of problems arose. So biostatistics is the application. This is getting a little too big. Let me. So biostatistics is the application of statistics to a wide range of topics in biology, medicine, and public health. It means that biostatisticians use mathematics, computer science, computational biology to answer questions and solve problems in biology, medicine, and public health. So we've gone through the same thing, except now it's basically application as far as statistics are concerned. And who are biostatisticians? So biostatisticians are specialists in the evaluation of data as scientific evidence. They understand the generic construct of the data and provide the mathematical framework that transcends scientific context to generalize their finding. And the reason why you want to generalize a finding is because once you develop a statistical view into a biological phenomenon, then you want to go into what is called as, and then you want to describe it, right? Graphs, bar charts, things like that, something that you did in your midterm, is something that you would, and that's called descriptive statistics. Okay, and then once you're through with descriptive statistics, then you want to say, well, can I make inferences to a larger data set of the same type or other data sets, and that is what is called inferential statistics. That uses a little bit of guesswork, right? Because you're going to project, for example, into the future. For example, you look at rainfall, and they use, when you predict rainfall, of course you have Doppler radar, you can see cloud, but then a lot of times when a weather people forecast weather, they use it based on a set of parameters, and if those parameters meet a certain point, they say, oh, all these parameters are kind of coming together, they're meeting those points, so it's like, okay, well, looks like we can forecast rain pretty strongly, because so that's inferential statistics, right? But in order for inferential statistics to work, you have to have a solid foundation. You have to have a solid foundation of information so that you can make inferences. Okay. uh, Biostatisticians play a key role in the design, conduct, and analysis of research studies and develop new methods to address emerging problems. Where statistics are used, obviously, clinical trials. Okay, we talked about randomized trials, blind trials, double-blind trials, in the giving of placebo. Then basically you look at a medication given to somebody, and it's like, well, what are the chances? Remember the log odd ratio. You gave the medication and it worked. You gave the medication and it didn't work. It worked without the medication, and you didn't give the medication and it didn't work, right? The log odd ratio is something you might want to calculate also. Epidemiological, that is now which expands to larger population. So it studies the causes, origins of disease in populations. They identify a group of people, monitor the disease, look for associations over time. And for example, you can look at COVID and whatever people's personal opinions are about COVID. And I think in very subtle ways, I've made my own opinion known. But at the end of the day, you cannot take away from the fact that there were symptoms, right? Symptoms which are all over the place, and the question then is, the epidemiological concerns would be, what were the pockets? Where were the pockets of the disease the most in terms of the symptom? Where were the deaths the most? Where were the hospitalizations the most? Right. So this is all epidemiological studies, and then for example, you might have small samples in order to study. You can also have, for example, purportedly it started in a place called Wuhan, and then they said, okay, then it traveled to Italy, and then it traveled to New York, and then it spread all over the world. So exactly the spread, the origins, when it comes to human populations, is epidemiology. And then of course genetic differences. When anybody's learned the foundations of genetics, and you learned about the Punnett square, for example, what are the statistical odds if you have a dad with brown eyes and a mom with blue eyes, okay, and then you have look at basically the alleles which are dominant and recessive, dominant, recessive, and so if the mother is recessive for blue eyes, that means there's a dominant blue eyes. The chances are 3 out of 4 that the child will be brown-eyed. Okay, so again, the foundation, and again, I'm just using a very, very simple, naive example because that's the Punnett square is when people learn the first things about kind of the distribution and the evolution of traits. Look at genomics, for example, the activity of genes associated with disease and treatments. And again, the moment you start going into large numbers, then it becomes an ensemble. Again, the spatial studies, geographical distribution of disease and risk factors. And last time I gave you a very quick rundown of clinical informatics, but there was I had a guest lecturer once who actually was actually studying COVID in terms of its distribution across the United States and kind of pockets where the disease was widespread and things like that. Okay, so statistics allows us to learn some of this. Okay, so now let's go back into the definition of statistics. So statistics is the discipline concerned with designing experiments and data collection, summarizing information to aid understanding, to drawing conclusions, and then taking the information that you have and estimating or predicting the future. Okay, so statistics are really important because you often hear of this thing, the trend lines, right? It's like, well, if something is increasing, it's going to increase, unless kind of a mitigating circumstances forces the trend line in a either different direction or the trend line to change directions. Okay, once again, we are still in the introductory phases of this class. So the interpretation of evidence linking environmental factors and disease, design of experiments, effectiveness of pharmaceuticals. Once again, we are looking for, you know, what are the chances, how many people got side effects, how many people did not get side effects, what are the conditions, what did some of those study participants, were they completely healthy, did they have some preconditions. All of these are things which kind of confound the issue, and statistics is a way not to cure it but in order to for us to be able to understand it. Okay, opinion polling in politics, obviously you do that, right? They always say that, well, a Fox News poll will weight Republican respondents in a higher thing, and therefore the numbers will always come in the favor of Republicans. On the other hand, some other polling organizations will do the same thing with the Democrats, so the Democrats also always appear, right? Also remember, when you always talk about numbers in terms of error bars, right? Because you want to talk about it in the context of standard deviation. Okay, then also when you look at you look at this idea of sampling, and sampling is really important because sampling is allows us to then extend to a population. Okay, warranties, improving the quality of an manufactured item, weather forecasting, we've talked a little bit about that, analysis of stocks, prediction of stock market prices. This is a big thing. Statisticians play a big role because how a stock will do, how much to invest in a stock, how much to divest a stock, how much to be bullish on a particular item or a particular stock, how much to be bearish on a particular item, when to sell, when to buy, etc. All of these things are based on prediction. Now you could take, for example, and don't know how poker is played, but I understand some of the fundamentals of poker is you basically guess, right, what combination of suits the other guy is holding, and that is based on how many, what cards are discarded, and then you calculate the statistical odd of a number that's not discarded, and what does your opponent, what kind of thing does your opponent carry. And this is from somebody who knows nothing of the game, who has never played the game. I begin to understand that a combination of cards is more valuable than another combination of cards. Okay, now some other concepts that you need to understand in biostatistics and statistics. You have a population, okay, that a group of people that you're willing, and that this could be an entire country, this could be the entire world. Okay, it basically is a preset group of people. What is a sample? A sample is a subset, and a sample is a subset because you're never going to be able to say, I'm going to poll 1 billion people, right? If it's an opinion poll, if it's a poll, if it's a political poll, you're not going to poll all 375 million United States citizens. So what you're going to do is you're going to poll a sample, and the point is that the sub is not just a it's just not a physical subset of a saying that, well, 100 people is representative of a billion, but it's actually represented, right? So for example, if you say there's just again to just drive this political point home, if there are Republicans and then there are Democrats and then there are independents and then there are libertarians, each of these that distribution, so let's say it's about 40 of each, and 15 independents and 5% libertarians. Then if you're really a proper representative sample would be 80 people, 40 of who are Republicans, 40 who are Democrats, 15 of whom are independent, and 5% of whom are right. And you would say, okay, those people, if I basically poll those people, obviously in an honest way, which almost never happens. If you poll those people in an honest way, those results you would say are pretty representative of the political temperature of the country. All right, let's look at the measurement. So the what you're measuring in terms of a numerical value is called the measurement. The property that is being measured is called the parameter, and a statistic is a number computed for the property or the sample or the population. Okay, so once again, some other concepts in biostatistics and statistics. Statistics, now we've seen, is of collecting, displaying, disseminating information, and then drawing inferences from the data. Then there's descriptive statistics, which basically displays and describes the data in a kind of, it's like, well, I could write, and now AI does this too, right? Gemini and all of these other groups, they do that. What they do is they will when you ask for a certain information and it's a large amount of data, then there's a little button which says, would you like me to summarize that data for you? Okay, and so for example, what is descriptive statistics is, you could read 10 pages on trends of a certain thing, for example, the sale of a particular product, or you can say, I can look at a graph and in 5 seconds tell you exactly what the trends are, right? Same thing with the bar graphs, right? So that's descriptive statistics, and of course the error bars and things like that. Inferential statistics is associated with drawing conclusions on the available information to a sample and then when it's extended to a population. Okay, some other concepts in statistics, qualitative statistics, more data, more description that do not have a numerical value. Okay, for example, polls. I mean, though polls are, so you always deal in percentages, right, with a standard deviation of so and so. And a quantitative is where you absolutely have to have a numerical value, and that is measurement. So the polls are more about trends, whereas, and then they always say, well, we have the poll on the first of the month, and then you look at the graphs and it's like, well, where does one party have it increased? Did somebody do something in the election? Do somebody do something, something notorious? And then you see the trends go up and down, and the trends hold, and somebody gives a speech during the convention, and then the polls, you get a spike, and then the next person, convention people, then the other party gets a spike, and so all of these are, which tells you what has gone on in terms of the trends, right? So, but measurements actually have a numerical value. All right, now let's begin in terms of kind of the beginning of how does one represent the data. Now this is data, right? And the point about basically converting into descriptive statistics will give us a kind of a snapshot view of the data. Now this is not easy, right? So for example, 21 randomly selected students, uh, and they are the ages of 21 students, right? So you see 18, 19, 19, 18, 20. You've met somebody, 21 students, and you say, hey, what's your age? They tell you their age, right? Now, and that's basically written exactly how, for example, people are interviewed. All right, so how do we go about making sure that we have a better way of representing this information? Well, that's the data as collected in that random sort of way that you met these many people, you told them their ages. Well, one of the things that you can do is what is created is creating a frequency table. So you know that the range of ages are from 17 to 21. Is that correct? Or 22. And then what you do is you basically write the ages from 17 to 22. Oh, I'm sorry. There's a 24-year-old too. This is why looking at this table allowed me to go back to the raw data, right? So there's 24, and then what you do is you create a frequency table. Well, one thing you could have done in between this point and this point is to write them in increasing order, right? So 18, all the 18s, all the 19s, then all the right up to whatever 24, right? But a better way to do it would be to create what is called a frequency table. You write all the ages, and you say how many of these are there. So right away you can see that the youngest age is 2017 and the oldest age is 24. But then you can see right away that that just from one glance of it, you'll say that look, the number of 19-year-olds, number of 18-year-olds is high, and after that it's the number of 19-year-olds, and then the 20-year-olds, and then the 17-year-olds, and then the 21 to 24, 21, 22, and 24 is just one person of that particular age, right? And which would make sense in the sense that most times a freshman in a university are typically between 18 and 19 years old, and then there'll be these these up and comers who are 17, and then there will be people who potentially took a break after high school, got a job, and came back to work. Okay. But you see how it goes from just a hodgepodge of numbers to potentially somewhere in the middle where you would line them in increasing order, but a frequency table tells you something a lot better. Now let's take a step further and say here are the exams, results of the exams, and I'm not going to worry about it other than to make a point. Some 30 students took exams, and you can see that the ranges are from really poor, which is like a 25, to about two people who got 100, and then there's a bunch of people in the 90s, etc. And one way to represent it, which eventually becomes your bar graph, but we'll see how we come across it, come about it, is basically create what is called a stem and leaf diagram. So this is the stem, and this is the leaf that arises from the stem, right? So what you'll see is this is 20s, 30s, 40s, right? Now, though this is like a zero, zero doesn't mean more. That this means that 440 is a score, and there's nothing here, which means there's no student who gets anywhere in the 30s. But you see, most of the grade scores are in the 70s, right? So 73, somebody got a 77, 73, 76, 70, 73, 73, 70, 71, 78, and 74, right? And so you see that's how, and clearly you can see two people got 100. So first of all, you write these numbers down in exactly the order that you see, right? But you break it up into the 20s, 30s, 40s. So right now, clearly, this stem and leaf presentation is a lot better than this. Okay. Now, the better way to do it, obviously, is to all these numbers that are there, right? These numbers that were there, you basically write it like you order them, right? So it's almost like 70, then 71, then 73, then 74, and that's done in this way. Now this is a slightly better in the sense that it seems a lot less random, and it's a lot easier to say that here. And just take the example of 70, which is illustrative of everything else. You will say, well, two people got 70, one got 71, three got 73, one got 74, and then one each got 74, 76, 77, 78, right? And you could say one person got 68 and two students got 69. So when you order it, right, if you order the stem and leaf diagram, then you get a little better picture. And so that's the point of descriptive statistics. You get a better snapshot view if you reorganize the information in not just a way that you can see it, but also reorganize in such a way that you can extract information without a lot of time. Now, that you can do this in this particular situation also. You can extract the information, but it's a lot better when it is reorganized. And that's kind of one of the point of statistics. Now, if you turn this on its head, right, for example, if you take the stem and leaf diagram and make it vertical, you basically get, and this is for the same data. Okay, now you'll see that more people got in the 70s, people got 90s, and you can see two people got hundreds, right? Two people got hundreds. Now this is not just One is just people who got from the 70s to the 80s, right, and the 60s and the 70s, and so you'll see that that basically a stem and leaf. When you make it vertical, it becomes a histogram, and there is what is called a relative histogram. So, for example, this is the actual number, and when you divide this number by the total number of people, then you get a relative. So a frequency histogram and a relative history of a histogram, almost like kind of it sums up to a percentage. And then what happens is now we are slowly going from, again, remember the point of statistics and the point of using a sample is so that you can predict, project, right, infer for a population, right? Otherwise, as going back to the poll analogy, we would have to poll 375 million people, find out what everybody wants, which is not feasible. And that's where statistics comes into play. So now when you look at the sample size, so here you have a small sample, and so you can see the shape of this. And then when you get a medium sized sample, you get a shape of this, right? You get a shape, and again you see the distribution. Eventually, when your sample becomes very large, you get a shape like this. And when you have a very large sample, that means all of this, like the individual demarcations in these bars, go away, and this becomes a smooth curve. Now, some of you might think, wait a second, now this is not, this doesn't make a lot of sense, because, well, but this looks like it's constantly rising up to that middle point, but here it's not. It's kind of going up and down. But eventually you'll see why the sample works the way it is. And there is something called as a Galton board. We'll look at that. We'll look at that, and that'll tell you why this kind of distribution is actually universally acceptable. Okay, it's the nature is that your middle point is always the one that is the one with the highest frequency. All right, simple formulae. For example, this is an average. Okay, that means you add all the terms divided by and you get an average. And then when it comes to in terms of the notations and the terms, when you go to when you look at this is a sample. When you go for a population, the X bar with a bar on top of it, right, is again addition over a large population, and the average notation is the Greek letter mu. Okay, for a large population, is the Greek letter mu, and so there's that. Now, that's the definition of a mean, which is also the average, and then you have the definition of a median. And when we looked at statistics, we looked at the LD, the sorry, the the value of 50 with the contiguous sequences, and we talked about what is called a weighted median. And that time I kind of also gave you an example of what a weighted average could be. Okay, so what is the median of a sample? The median of a sample is basically writing everything in increasing or decreasing order, and the middlemost number is the median. Sometimes you can have the median, and if you have an even number of terms, the middle two numbers divided by 2 would be the median. In an odd number, it's fine because you have a middlemost number with an equal distribution on either side. So similarly, here you have a relative frequency, and the median again is the middlemost number, irrespective irrespective of the frequency, right? And that's one of the reasons why when we calculated the 50 and how many contiguous sequences, um, uh, that was we had to have a weighted mean because it was much more representative of the average. Now you can also determine skewness. If, for example, you look at again, we are looking at relative frequencies, and you look at the median, which is x with a tilde on top of it, the curvy line, and x bar is the median. So when in if a relative median, skew means how does the median separate from the mean? Okay, how different is it? So in a properly defined thing, you have the median and the mean are the same. That the middle number is also the one with the most, which is also the average. Here you have the exact same situation, However, you do not have the frequency of the median, and the mean is not the highest. You have higher frequencies on both sides, but you're still going with the average, right? And this is where what is called a uniform, this is what is called a uniform distribution. A uniform distribution, okay? Now, when you have the skewed, when you have things like this, you will see that the mean trends here and the median is the middlemost number tends here. If on the other hand it's skewed in a different direction, then you will have the mean is here and the median is higher than the mean. So you'll also, when you compare the median and the mean, depending upon how the data is skewed and how the data is calculated, you'll have a different distribution and the values will also be different. Okay, what is the mode? That's the three M's of statistics: the median, mean, and the mode. And the mode is something where you have the highest frequency. So the terms that are the most, like in the when we looked at our stem and leaf diagram, the modes would have been the one which is in the 70, the one with the highest frequency. So here what happens is the relative frequency of whatever measurement this is the highest. Let's say rainfall in June, and in the other cases, whereas the median and the mean are likely going to be here, the mode is here. All right, now let's look at variability of the data set, and the variability of the data sets points to something else we know, and that is the standard deviation, and the square of the standard deviation is called the variance. Okay, all right, so here you have one data set and you're plotting it. So it goes from 40, 38. So what's the lowest number is 38, and the highest number is 43. So here what happens is, if you do a dot plot, right, 38, and you plot each of these points, you'll see the same distribution, right? You see this distribution. On the other hand, when you look at this thing, notice something, that they are kind of clustered around the same mean, right? But but see, if you at first glance, if you look at both these sets of data, you will find that, well, they look like numbers in their 30s and their 40s, right? That's the first thing. But if you really look at some of this, you'll find that this data is a lot more precise. Precision means it's clustered very close to the mean. On the other hand, this is spread out. Okay, so again, a graphical representation of data will always give you a better picture, and you'll be able to grasp the point of the data a lot more quickly than if we were looking at these numbers, right? And that gives us the definition of what is a range. If you take the difference between the highest value in the data, the numerical value, and the lowest numerical value in the data, you get a range. So here you see the range is very small. So this has very small deviation, right? Deviation means how much apart is it, away is it from the mean. So you can see here the range is high. So you go from 38 to 43, which is 5, and then here you go from 33 to 47, which is 13, 14. Okay, so that's so again, there's nothing here which I'm teaching you which is not something you've already learned under different in different backgrounds and concepts. Okay, so but it's a good idea to kind of get past some of the fundamentals here. Okay, so now let's watch the Galton board. Okay, so let's watch the Galton board. Can anybody hear that sound? Hear that? Did you hear that sound? No. Okay, never mind. So, um, I will show you the Galton board. In this particular case, you don't need. In this particular case, you don't need the sound. But I will open my. Okay. So let's take a look at the Galton board. Okay. Now let me stop and kind of talk a little bit about it. So the Galton board. So here you have a bunch of. See, what happens is, if you expand this, you will see that the Galton board has, this guy is going to drop a bunch of ball bearings into this, okay? So you'll see these are all ball bearings. Now, when you rotate it, um, when you turn it over, all these balls will start falling, right? But here what happens is, these are the little separation the board is built of, which means that every ball bearing, once it strikes this, it's going to go either left or right. So at every one of these points, it's a statistical order of going left or right, right? So there is no bias in the system at all, because it can go left or right. So the question is, and I'll let the video play. So now he's going to pour these, and you see that though it's a fair distribution, everything is falling from a single spot, it doesn't really matter, right? Give or take a few things here and there, and he's going to try it 3 times just to kind of prove a point, is that the distribution, now in slow motion, that every little thing it goes here, it can go in either direction, but somehow they all cluster into some sort of a mean, which is in line with this, right? So again, they are not exactly the same way it falls, because that's the way the statistics is. But the honest way this thing works is, you actually have and I'll come to this part later. You will see that it somehow, that's the kind of the nature of the distribution. All right, let's keep going. Again, very often you use these two words, accuracy and precision, interchangeably. Okay, you say, oh, it's accurate, it's very precise. But that's not necessarily true, because now we're going to learn the words in the proper term. So accuracy is, there something has a true value, and how close it is to the true or accepted value is is close to the true or accepted value, is the accuracy, right? Now, precision, on the other hand, is not necessarily close to the true value, it is close to the mean. So you could have something which is, you expect, and something is very precise, it's also accurate, but that's not necessarily true, because because let's say, I'll give you an example, okay? Let's say that you have, you have a target, right? And you throw a dart at the target, right? Now let's say that everybody has to stand at a particular point, okay, at a particular line drawn on the floor, and you throw a dart at the target. And we know the target of the dartboard, right? It's like it's bang in the middle. Problem is, so let's say, for example, if I get a whole bunch of people, all of them are left-handed. And because they're left-handed, let's assume that there is a certain bias in the way they throw, right? Now, you can see this as right hand, but I'm actually holding my left hand. They throw it using the left hand. Let's assume there's a certain bias, right? That left-handed people, because of the positioning of their hand, will throw. So what's going to happen is, even if they're strong throwers, right, because of the left-handed bias, they are going to throw. They're going to basically be slightly off target, but then all of them, because of that natural bias, and assume that everything else being the same, they will they will all cluster. The darts will cluster around a certain spot. It'll be away from the target, but it'll be clustered around the same spot. Let's assume that, everything else being equal, left-handed throwers have a certain bias, just because of the nature of their, because of the nature of their throwing, okay, or the nature of their left-handedness, for example. So what happens is, you're going to have a whole bunch of darts clustered around one spot, but it won't be close to the target, or it might be slightly away from the target, right? So then what happens is, that is not an accurate throw, because accuracy meant that you had to throw the dart at the basically the a bullseye, right, in the bullseye. But they have thrown it slightly off to the right, but everybody's thrown at the same spot. So, but if you take an average of that position, you'll find that all the darts are very, very close, and that means it's going to be something that's highly precise and not necessarily accurate. Okay, Some other words that you're going to learn is again this. Now most of you probably don't remember any of this because it's just stuff that you put in your Excel spreadsheet and then it jumps out at you. Okay, but it's a good idea to remember these. So let's go with this definition first because this is what is called the standard deviation. And the standard, so basically what you do is you take the deviation. Every deviation means the actual numerical reading, the observation, minus the subtracted from it is the mean, right? Is the mean, and subtracted from it from you subtracted from the mean. Now you can be on this side of the mean or that side of the mean, right? And to mitigate that, to take away that issue, you just say I'm going to take the square of it. I'm going to take the square of it, which means you don't worry whether you just worry about the deviation, how far is it from the mean, but whether it's positive or negative shouldn't really concern you because you're just looking at the absolute value. So you take the square of it and then you sum all of that and you divide it and then you divide it by the number of observations and so this is basically what is called the variance or the population standard deviation. It is slightly different from the sample standard deviation, and that definition will show up quickly. Okay, so I'm sorry. So you'll see that this is the population. Okay, this is the population, and this is sigma. Sigma is the standard deviation for a population. For a standard deviation for a sample, as we will see in the next slide, is going to be S. And then what you do is, so you take this value, you get the standard deviation of a population, divide by the population size, and the variance is basically just the square of the standard deviation. So you can either calculate the standard deviation and take the square of it, or you basically just take away that square root sign and you get the variance. Now, if you go to a sample, you actually the formula is the same for the variance, which means standard deviation, except you take the sample size minus 1. And the sample size minus 1 is what is called as degrees of freedom, which are not important in a population because they don't change anything. But in the case of a sample, it's really important. So let's look at this idea of what is degrees of freedom. And meanwhile, feel free to interrupt and anyway. So let's look at variance and standard deviation once again. Okay, so here you have your relative frequency like you've seen, and then you have the mean, right? And then you have standard deviation. The standard deviation means that it is one standard deviation away from the mean. That means it encompasses this much of the data, right? This much of the data. If you have two standard deviations, which means that if you just take into account this much, you have about 68% of the data. And okay, this has actually been calculated. 60% of the data, which means 60% of the data is is close to the mean or highly precise data. If you can calculate two standard deviations away, that means the standard deviation plus minus twice whatever your mean plus minus standard deviation, then it takes into account this much of the data. If you go three standard deviations, that means you're going to take like 90 some percent of the data. Okay, and that's how these standard deviations are calculated. Now there is this, so which means that if you say that all the measurable data, okay, without any outliers, without any errors, without anything. Now this is what is called, this graph, I'm going to use a word, may have not heard of it, is what is called asymptotic. Asymptotic means that all the data, all the measurable data is considered here, right? Is considered here, which means that this graph, when you say it's asymptotic, it gets very close to zero but never hits the x-axis. Okay, which means it's impossible to take for a particular population, it's impossible to make any errors. It's impossible to make any errors or to be completely error free. Okay, that means all of your data is basically considered within this. You're not really losing anything in terms of errors. Now, those of you who have heard of what is Six Sigma, right? Now, again, you go to a business company, a management company, and they say, "Oh, you're going to take Six Sigma training. You're going to be a Six Sigma green belt, or you're going to get a Six Sigma black belt," which means you're going to be trained in order to within that system in order to minimize errors, which means all your accurate data has to be within Six Sigma standard deviation. Now, because this never goes to zero, it means you're never going to have error free. But the moment you go Six Sigma, which means here, 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 and really far out, which means that your errors are going to be very, very, very tiny. Your errors are going to be very tiny, almost zero, but not quite zero, right? So Six Sigma training is a statistical device or methodology of basically improving your processes or improving your management style or improving your business style or improving your customer service or everything with as little errors, which means that all the correct, accurate information, error-free information has to be contained within almost 100% of the data, which means you might have very small. Now, the reason I have this particular slide share is because it actually hits very close to home. Okay, and I didn't grow up in Mumbai, but I spent most of my youth studying, etc., in Mumbai. And I'm going to give you an example of something really unique. You probably never heard of it, but it's basically it's a business model which is beaten Six Sigma to the point where Google and all the top investment companies and all the top management companies and the law firms and accounting firms have tried to study this system composed of people of this business system of people who are basically have no literacy at all but have error rates that are so small. It's identified as a Six Sigma organization that major companies, multinational big time companies, tech companies, etc., are trying to learn this system. So because we are looking at this idea of Six Sigma, let's basically look at this particular slide share. Now, I'm just going to go from this slide share. Now, this is what is called as the Dabbawala. Okay, Dabbawala. Now, Dabba means box, and Wala means a guy who carries around boxes. Now, this is again, so a lot of you, this whole notion will be completely new. Okay, so bear with me. None of this is going to show up on the exam. You don't have to remember any of this, but this is an organization. So, who are these people? So, let's say in India, now, of course, the trend is, not especially in Mumbai and places like this, all the people who work, okay, let's call them men, and the women used to be, like homemakers and things like that. That trend is changing, so don't get mad at me. Um, what used to happen is people used to go out into the office, and the offices used to be downtown or in different parts of the city away from home. So you actually had to take, now people drive cars, but you had to take a taxi or you would take, but you couldn't do that every day. So you would take the local train, which is the most efficient system of the Mumbai Railway, is the most efficient railway system in the world. uh, uh, Very crowded, but the number of people that need to be transported. So this is not a whole Indian transport system because that's not anywhere close to being the best in the world. But in terms of sheer efficiency, just in the city of Mumbai, the amount of number of people that gets transported from suburbs as far as like an hour and a half away right into the city where everybody travels for education, school, etc. Okay, so the fundamental idea is that people used to go out to work and they need a home cooked meal. Okay, the question is, how does one get the home cooked meal to those particular people? So this group of people, these guys here, are they kind of look the same. They come from very remote parts, very sturdy farmland type of people who will actually come to your home, take that lunch box, which is multi-tiered, and multi-tiered because Indian Indians being what they are, is like you're basically going to get a whole meal. So it's not like, hey, just throw a bunch of cheese, a bunch of sliced meat between two slices of bread, and that's you put it in a Ziploc bag. That's not lunch. It is a full lunch, which means the rice, the vegetable, the meat, the other gravies, etc., all in one big stackable boxes. Okay, so this guy or this group of people will show up at your house in the morning, and they will take your box, get it to wherever downtown this person is working, but then an hour later flip the process around and deliver it back to your home by 5 o'clock in the evening, ready for the next day. Okay, so now since you understand the concept and I provided a little bit of context, let's see what happens. Okay, so Dabbawala, again, these are carriers of boxes, are an extraordinary group of more than 5,000 individuals in Mumbai. And again, I suspect that their influence is now waning because there's really good street food. People eat at restaurants. They're not needed anymore. So, Dabba just means a lunchbox. Wala means a transporter or the conveyman. So it's a lunchbox carrier. And basically, it's a stackable box in the tiffin because I said no self-respecting Indian would say, I'm just going to take a sandwich. That is changing now. Okay, so you have to, but I wanted to give you the basic idea of what it is. All right, millions in Mumbai commute to earn a living: banks, colleges, hospitals, government offices, private factories, blah blah blah. In a country where hot and fresh cooked home food is the most preferred for consumption, that is also changing now. Carrying of lunch boxes is a big burden for the working populace. Now they could, but you want a warm hot meal. Uh, so this is an association which is more than 100 years old and now probably more than 125 years old. So who are these people? They will lunch to 2 lakhs. Now what is a lakh? Oops. What is a lakh? 2 lakh people is lakh in India is 100,000. So 2 lakhs is 200,000 people get their lunch, but the work doesn't end here. When the thing is done, they also carry the lunch boxes to the homes of the customers. Now here's the part where you have that Six Sigma point. Only one mistake in 16 million transactions. Okay, so that means, and consistent. So that's what this ISO is, what is called the Indian standard, like of excellency or excellence or something like that. I don't know what the full form of this abbreviation is. So they've gotten a Six Sigma designation, and we know that because several people, several tech companies, top business companies are studying their methodologies in order to improve their own thing. Okay. All right. So what do these guys do? They, as you can see, they don't seem sophisticated or anything. They just seem regular. They wear this hat, which used to be called the Gandhi hat after Mahatma Gandhi. And here they have all these boxes around them. And the local trains in Mumbai have one compartment, one or two compartments, which have no, like, only seats around, so you can actually move these big containers in there, right? So it's actually designed for these guys. Okay, so it was set up in 1890, and it was basically used to carry food for the British, because remember, until 1947 India was still under the British rule. So this was a guy, okay, this guy, he started this thing, and in 1930 he attempted to unionize. Then it was picked up in 1956 by a charitable organization, and again, the current president, that might have changed. So here's, now these are just streets, these are just handcarts. I mean, we're talking about the most primitive things, right? So basically you'll see that each of these has a code, and a few slides later you'll see about the code. So what they do is, they don't get into the car or a van or something, because each of these has to be picked up from individual homes, and then they're brought to a particular center, and from the center you have a different group of people who load it onto these handcarts. So they're pushing all of them, and they push them right up to the train station. Then they carry the thing to the station, and then at the station they're met with other people or other people with the carts, and then they go to another distribution spot, and then it's taken by these same groups of people to all the specific destinations. Okay, now you consider the logistics of this transaction. Some person, homemaker, gives the food, it's expected to get to the right place with all these seemingly primitive methodologies. Then that person has to eat it, and an hour later the guy comes and they reverse this process, and it's home. Okay, all right. So so the question for their success, again, now you're beginning to use all the logistics engineering methodologies, supply chain, coding system, and the nature of the employees. So again, this is a single guy. Here's a here you will see, here's the train. It's moving, so it's kind of a picture is a little blurry, but he's sitting on the railway platform. So the way he's squatting means that, like, they are not people who are used to chairs and armchairs and things like that, right? And he had this cart is standing there, and he's basically pushed it from somewhere, and now this entire load, which he will likely carry on his head, is his responsibility. Okay, so shockingly, there's no IT, there is no databases, there's no computers, no nothing, nothing, nothing. This is purely based on kind of a handwritten way done by people who likely have zero to a very, very minimal education. All right. So a thorough level of practice, unwritten strides. There are 40,000 exchanges occur every day. So here's how it is, right? So you collect it at homes to one point, okay? Then one point you go to an aggregation point. It aggregates here. Then you go to the train station, and then each one goes to a different destination, and the destination has these aggregation points, and then they're sent to the offices. So you think about the logistics of this, all has to be done by hand. None of these guys have their own vans. They basically use hand carts, so it's just physical muscle. And it's still going on. I suspect the influence is a lot less now because you can just go down the street and get something to eat. So they either carry this stuff by feet or by foot, or there are bicycles where they've got on the carrier side, they've got like these things where they hook these boxes and the lunch box. So now, if you say, I'm showing up for my box, and the guy and the person of the house who's supposed to get the box ready says, well, hey, can you wait for 10 or 15 minutes? I'm not done yet. It doesn't work. They're not going to wait for you, right? And that's kind of the rules under which they work, right? So, so you have to assemble. You've got to pick up the food and assemble at the collection point at 9:30. From there, it goes to the aggregation point. From the aggregation point, it goes to the railways, to the local railways, and then it goes. So by 11:30, 12, the food is necessarily delivered, right? So again, aggregation point, then they go to the railway stations, and then it goes to the thing. Then from there's another group of people who will then create a distribution point, and then you reverse the entire process. Okay, so I'm not going to read every one of these, but here's the coding system. Okay, again, this is very, very simple coding. It's these, and each of these guys, they don't have to know everything. They just have to know the pickup point, right? The pickup point, they can know the code of where this is supposed to go, where this is supposed to be picked up, and they know their aggregation point. After that, somebody else does the work. Somebody else travels in the train, then the pickup point is somewhere else, and that's basically how it is. So you see, very primitive. There's no barcode. Nobody goes with a handheld barcode reader. No, nothing goes and sits in a database. It's basically a straight transaction like this. And so basically, this tells you it's a particular railway station. It tells you the name of the place, a name of the building, right? And then aggregation point number 5 and where it's supposed to go. That's it. But the point is, everybody does not have to know anything, everything. You just have to know, everybody just has to know their specific task, that specific point that they have to do it. They have to do it efficiently, they have to do it as accurately as possible. And clearly, in more than 100 years, now this is going to be about 135 years now, it's not, a system has not failed. I suspect it's going to be waning in terms of its influence and things like that. So this is the only code, and everybody who knows it kind of recognizes their code. Somewhere in here, they know what the aggregation point is, where the pickup point is, and then they can also use the same code to return it. Okay, so BVI is Borivali. Here's a code, a destination. This is the name of the building, the 14th floor. Can you imagine if you don't have an elevator? And then, so again, surname of the person and things like surname and last name. So you can see this guy is carrying their entire bag over on his head. Okay, they are all stakeholders in the organization. It's a very unique way of doing it. Most of the employees are illiterate. Okay, they might have minimum or no schooling at all, but they're very hardy guys. They're very hardy, very strong. You can see they have to push hand carts or carry it or go up and down stairs. Sometimes you might have 10 different buildings, and there's only one guy who's responsible for that area. So that guy goes up and down picking up these lunch boxes. They're employees, school illiterate, but all they have to know is know the code. And then they basically, and if one person is to pick up 20 buildings and then move it to a particular collection point, that's their job. Very very repeated. The next person takes a collection point to the aggregation point, that's repeated. Then the person from the aggregation point takes it across the it's not like you don't dump it into the railway compartment, into the trains, into compartment of the train. You actually have to stay there. There are people who carry it across, right? And so that's kind of the process. So 3 hours completing assignments, 60 to 70 kilometers on foot, uh, bicycle carriers combined. You're not allowed to drink. Okay, 6,000 is the equivalent of $60. Okay, of 60 dollars a month. Now, it's probably higher now, but $60 a month. So you can see. So you see this. You see the mechanism of this, right? This is one guy. This is the other guy. You see, this guy has got a little red thing. It's just kind of a little thing of. It's temporary. Just roll some cloth and keep it so it doesn't hurt your head. Now, what's going to happen is they're both going to lift it. They're both going to lift it, and then this guy is going to scooch under like about here, and then once properly balanced, the head load, he's strong enough to now carry it on his head. And you can see these are the local trains on either side. Okay. uh, 36 crores is 36 point some is 36 crores is I think 3.6 million dollars. Okay. Uninterrupted service, doesn't matter whether it's bad weather, whatever, the food goes there. They're well used in local areas, okay, to save time. No errors. Every lunchbox changes hands 6 times. Okay, 3 times before it gets to the person, 3 times on the way back. And they know this. No, do not take a break, rest. They do not use modern technology. There have never been a problem with management and union. It's a Six Sigma designation, and the accuracy is 99.99%, which means, right, that means you're really beyond, any error is beyond Six Sigma. Okay. Cost of service. So if I wanted to do this service, this is probably more now. Again, this is a little dated. 450 rupees a month is the equivalent of, I don't know, $5. Okay, but this is likely more, and customer service is 100%. Okay. Uh, Now they have done some other things. For example, like if the food is not touched, if the guy is like, "Hey, I don't want to eat it," or "I don't want to eat it," they have when it comes time for the collection point, they have now partnered with a charitable organization that feeds hungry children and things like that. So what they do is, like, if somebody says, "Hey, I got the box. I don't want to eat the box. I don't want to eat anything," they will put a little sticker on it which says uneaten, untouched. So then there will be a collection point. People from this particular, from this social service organization will actually pick up the boxes that are untouched and then save the food for the. Okay. So again, you feed a lot of people from the slums. It's more than 200,000 people. So they are basically partnering with these charity, right? So food that is never eaten, barely touched, rather than wasted, they decided to save it. So again, this is kind of the point. See, so you have that what's called a share sticker, which means they know exactly what, so the social workers, they will come and they'll pick up that the food. Share means that it's not been eaten, and they will take away the food in separate containers to give to the children who are poor and hungry. Okay. Brilliant creative way of addressing the problem of hunger. Now, what you see here is again not immediately necessary, but so India was independent on the 15th of August 1947, and by January 30th of 1950, the Indian Constitution was written, and that Constitution is what is called as Republic Day. Right, 3 years later, they wrote the Indian Constitution, It was styled on the U.S. Constitution. It was styled on the British. The British have what is called an unwritten constitution, but they use their, even things like the Magna Carta and things like that were used in the creation of. So basically, what happens is, and this is New Delhi on a winter morning, and first, of course, you're going to have a march past of the soldiers, the various army units and various air force and navy units will march, and then you have like it's a cultural parade. Okay, so organizations, groups which are really crucial to the kind of the cultural functioning of the country, so they are often celebrated. And so you can see that once you see these guys were allowed to march, so basically it was a celebration of this Dabbawala organization. Okay, and that's basically the point of what I wanted to say as far as this was organization. But I deliberately wanted, because it hits close to home. It's something that's dear to me in the sense that going to school, going to work, going to college, you see them, they're ubiquitous. You see them all over the city. You travel in a train and the compartment is too full. We'd kind of go into the compartment meant for it was called the luggage van, and you would see these guys. You see them all over the place. Really hardy guys come from rural parts on the outskirts. So they would typically, probably wake up at 4 in the morning. And my apartment building was very close to like about a 5 minute walk from the railway station. So it was a very, very highly trafficked area. And so, anyway, I gave you a little glimpse of my personal life too. But again, this is an organization. Now, I could have, used in this particular class shown you talked about the Six Sigma, green belt, and black belt. But that whole thing is how much do you take into account all the non-error data is contained in that graph, and the very last dregs, which is almost zero, is what are basically your error rates, right? So if you say my error rates are up to one standard deviation, which means that 68% of your that means 30% of your work is in error. So the greater your standard deviation that you go beyond, the the that means you are encompassing more of the errors. Okay, so this was supposed to be a quiz, but I'm not going to worry about this quiz, so feel free to ignore it. Now we're going to look at some other okay, you know what, take about 5 minutes and come back, and we'll do more. Okay. Okay, everybody back? Let's go through some additional concept now. Because you guys can't, because you guys can't listen to YouTube for some weird reason, we can try, but because you can't, I'll just there's two more videos which actually explain things in a way that much better than I could for a particular concept that we're going to cover. So I want you guys to like um, if we can't, I'll send you off to watch the videos. 10 minutes later, come back and then we can continue. Okay. So, but before that, we'll try. We'll see what we can do. Okay. Some more definitions of in statistics. One is percentile, not to be confused with percentage. And again, those of you who've taken your SATs, GMAT, GRE, etc., you you probably know the meanings of what percentile, right? I was in the 89th percentile. Um, so again, just to give you the broad definition of a percentile, is so if you say I'm in the 90th percentile, it means that the people who took that test, 90% of those people scored equal to or lower than you. Okay, that tells you you're in the top 10%. So that's a percentile. So a definition of percentile, given an observed X in a data set, X is the pth percentile of the data if the percentage of the data that are less than or equal to X is P. Okay, and that's the easier way to explain that 90% got equal or less than, therefore higher percentile obviously is better. Other kind of definition is what's called a quartile. And in a quartile, so for example, what you do is you take your distribution, which is your Gaussian, your standard population distribution, and you break it up into four parts. Okay, four equal parts. So you will have basically Q1, Q2, and Q3. So between Q1 and Q2 will be 25%, Q2 and Q3 will be 25%, beyond Q3 will be 25%, and before on other side will be 25%. And the numbers you can see are X min, the minimum, quartile 1, quartile 2, quartile or Q1, Q2, Q3 values, and the X max. So you will have 5 parameters to measure, but you're basically taking your data and breaking it up into 4 quartiles. Now, if you kind of took a drone above the graph, right, and looking down on the graph, you can actually take the quartile and basically create a box plot. Okay, and a box plot shows you the data as if you were kind of sitting on top of the graph and looking down on it at each of the quartiles. So again, you can think of this distribution as a Gaussian where it goes from minimum and then it goes to the high point, and I'm actually with the mouse I'm actually tracing the this particular, I'm tracing the Gaussian curve, and the heights are at the point between at Q2. That is a maximum. Okay, so that's now this is very important to understand this concept of what a null hypothesis is. Okay, and when you look at the chi-square tests and all of the other things that we're going to introduce in this class, we have to understand what a null hypothesis is. So a null hypothesis says that no statistically significant, very important to even kind of contextually and conceptually understand it. A null hypothesis is a hypothesis that says that there is no statistical significance between the two variables in the hypothesis. It is the hypothesis that the researcher is trying to disprove. Now, let's look at it from the proper perspective. When you do an experiment or you conduct a particular hypothesis, you actually go into that hypothesis with the idea that there exists a statistical significance between the two variables that you're trying to study. Okay, that there is. But when you nullify that hypothesis, you're actually stating that okay, I got it the other way around. when you're studying two parameters, let's say temperature and wind, to predict rain. Okay, so these are the two parameters. Let's keep it simple. Just keep it temperature and wind. Okay. Now, you go with the idea that there is no statistical significance. That means that you go with the idea that it's a null hypothesis, which means the temperature and the wind, these two parameters together, have nothing to do with the rainfall. Then, when you have disproved it by showing that temperature indeed has something to do with the rainfall and the wind indeed has something to do with the rainfall, I'm just making this up now, that means you say I basically disproved the null hypothesis. Okay, so you start out with the premise that there is no significance. Every time there is no significance, and when you disprove it, then you say I have rejected the null hypothesis. On the other hand, if you say, yeah, that's right, temperature and wind provably have nothing to do with rainfall, in which case you say I have accepted the null hypothesis. Okay, so remember, forget about forget about the notion of saying, well, I hoped, and and I created my hypothesis based on hope. That is a human emotion, right? But from a statistical standpoint, you say, I want, I'm going in with the premise that there is no, I'm going in with the premise that this is a null hypothesis. That there is no statistically significant reason why these two parameters or the single parameter is associated with an observable or an outcome. Okay? Then, on the other hand, if that is proven, then you say, okay, I accept the null hypothesis. If it's disproven, you say, I reject the null hypothesis. Okay, so important to understand. Uh, Now, again, you can also go with the correlation does not imply causation idea. Now, if you basically, when you do your work in trying to prove or disprove your hypothesis, if you then have a statistical significance between the things you're measuring and the potential outcome, you say, I have an alternative hypothesis. Okay, so you premise your entire point by saying there is a null hypothesis. Then you accept the null hypothesis. If, on the other hand, you reject the null hypothesis and show that there is a statistically significant correlation between whatever, then you say, here is now my alternative hypothesis. Okay, so the default is the null hypothesis. Now, I don't know how many times I'm saying this because I want to try to hammer home that point. The default is a null hypothesis which you can reject in favor of an alternative hypothesis, or you can say, I accept the null hypothesis as binding. Okay, so once again, all of that I tried so many times because I'm a little hesitant whether you guys understand what I'm trying to say, but that is basically it. Okay, so let's some examples of null hypothesis. So again, you start with the premise. Your default is that the hypothesis is null. So you say hyperactivity is unrelated to eating sugar. And then you see, you conduct an experiment and you give a bunch of kids, your control group, vegetables, and you give and you give high fructose corn syrup candy to the kids, and then you say, okay, well, if all of them, even after eating the candy and then eating the vegetables, they all behaved in the exact same way, you say, I have to accept my null hypothesis, and the null hypothesis, hyperactivity, is unrelated. But if half the kids are just sitting in a very calm way and the rest of them are bouncing off the walls, then you basically have then you have a alternative hypothesis that is rejects this idea and says that indeed hyperactivity arises from an excess consumption of sugar. Okay, all right, now let's try another one. Plant growth rate is unaffected by the presence of cadmium in the soil. Unaffected. Okay, now if you got a bunch of cadmium in the soil and all the plants, okay, for example, so if you say I'm conducting two experiments, one is soil which perpetually has cadmium in it and the other soil does not have cadmium in it, and they both grow at the same rates, you say, oh, that is correct. Plant has nothing to do with cadmium. Plant growth has nothing to do with cadmium. On the other hand, if you see that the ones which are of soil which has no cadmium and then the soil which has cadmium, and one of them shows stunted growth and the plants are kind of half dead, and the other one shows a vibrant, luxuriant growth in plants, then you say, I reject the hypothesis that plant growth rate is unaffected, and I accept the alternative hypothesis that cadmium indeed affects plant growth. Okay, now we're going to look at another term that you typically see, and that is called the p-value. So the p-value is used to weigh the strength of the evidence, like what is the data telling you. So uh, a negative, smaller p-value, it's almost like a percentage value, right? Or a p-value is a probability value. If it's less than, it's between 0 and 1, and the closer it is to 0, that means you are rejecting the null hypothesis. The closer it is to 1, you are accepting the null hypothesis. Okay, so now let's take a look at it again. So a p-value less than 0.05 indicates strong evidence against the null hypothesis, right? So now p-value becomes a lot more important when you consider it against the backdrop of the null hypothesis. So you say when the p-value basically tells you that it is a measure of the null hypothesis. So if you say a p-value of 1 means that the null that it meets a requirement. Remember, the premise is always the null hypothesis default, and if the null hypothesis, the p-value is high, which means we're edging towards the null hypothesis. If the p-value is 0, which means we're edging towards rejecting away from the null hypothesis, which means that is we are considering the alternative hypothesis, which more often than not is kind of the opposite of the null hypothesis. Okay, and that's what this is. And so, for example, if the p-value is 0.05, then you really say it's very hard to tell from the data we see or the observations that it is something we have to reject. Okay, now we look at what is chi-squared. Okay, so again, now I'm going to try and run this video. But now all these are good. These are good, formulas and all that, right? But let's look at this video, and let me see if I can. Let me see if I can run this video. Okay, so let's go to our thing here, and now let's play around with this a little bit. So let's see if it works. Okay.
Calculus class. Do you have a hard time understanding your instructor? Do you wish there
You
was a
hear
simpler
it?
way? I get it. It's frustrating. You go to class expecting answers only to walk away with more questions. You lose valuable study time Googling homework problems, desperately searching for the thing.
Let's give it one more try. Can you hear? Can you guys hear? Okay. All right, great. Okay, I'm going to go take a look at the video. Thank you guys. Go take a look at the video and come back. Very, very nicely explained. About as nice, much better than I could. So, but you have to give props where they're due. So go take a look at this video and they'll come back and we'll talk a little. But he explains it in a really nice way using dice, okay, and coins. And we'll reconvene at about 10 minutes after 2, 3. Okay, everybody see the video? Everybody hear me? Okay, thank you, Michaela. Okay, very good. All right. So very useful, isn't it? Very useful. Very nice way of explaining. And Yuchia is trying to type something. Not quite sure what it is, but okay. All right. Well, thank you very much. Okay, so as you can see, the video is very good, very useful. And so what we're going to do is, so now this is the chi-square table, right? Again, you can get a chi-square table anywhere. So this is not an issue, but again, this you can use the chi-square table to basically get to that point where you can reject. Now here's the homework which is due. Don't worry about the 11:10 because that's still the fall slide. So it's due at class to next time, next week on. So that would be the 4th of July, August. Now the question is, in this case, in the case of the example he showed about the dice, you'll agree that he accepted the null hypothesis. Agreed? Okay, so that is the case of accepting the null hypothesis. What I want you guys to do, and you can write a program, use Excel, do it by hand, I don't know, is come up with, for that same experiment that Mr. Bozeman did, okay, Mr. Anderson, I think, also Bozeman did. For the same experiment, I want you to come up with a combination of dice, same experiment, same conditions, where you would go from, it would push you from accepting the null hypothesis to rejecting the null hypothesis. Now, in here, the critical term is just. Okay, just, which means you have to tell me what combination would just go from accepting to rejecting the null hypothesis. Okay, so that number that he calculated for a chi-squared, what would basically, you accepted the null hypothesis. Now you have to come up with a combination of dice that would go from accepting it to rejecting the null hypothesis, showing that there is a statistical significance between the observed and the calculated, the throwing of the dice. Was that the dice or was that the coin? That's the dice problem, right? Where he had 6 dice, or was it? Yeah, it is dice, right? Yes. So 36 dice, that's correct. So yeah, let's go with the 36 dice problem. Now, he went from determining the dice to 36 dice, and he basically tossed them and he calculated them. And so in that dice, so what combination of dice will give you a chi-squared value? And that's the one you have to calculate. Now the operative point is just, very, very important, because because you can calculate some combination and it'll give you some outlandishly huge number and you said, there you go, I have now rejected the null hypothesis. I want to get to that border, which means you've got to come up with all these combinations, and the lowest of them, which is above that little cutoff, where you actually have to accept it, you have to reject it, the lowest of that point of the many numbers is the one you're supposed to aim for. And the further you get away from, and I know what the lowest number is, the lowest possible number is. So the further you get away from it will take away from your points. Okay, so this is due on the 4th. And again, look at that video again, come up with different numbers. And if you send me something early, I'll tell you how far or how close you are. But that depends upon your personal effort towards it. Okay, any questions about this? Anything is not clear? No, I just want the chi-squared value, the chi-squared value which will just push it into that rejecting and all. I don't want the table of answers. The table of answers is something you can come. Now, if you want to include that in your homework, that's fine. Or alternatively, you can give me a number. No, I'm not looking for a single sequence. Look, he used the dice combination. Let me be clear about this. He used the dice combination to come up with a chi-squared value. Then he put it in the chi-squared table for the number of observations, 6 or whatever, right? He put those number of observations and he came with a chi-squared value. And he happened to be on the lower side of it, which means that he had to accept the null hypothesis, that there was no statistical significance. You want to be able to get to that point where it's just above a combination. So I'm not looking for the sequence. I'm looking for the chi-squared value following your combination. Right, he said 9 something. So Michaela, you're right, and you helped your classmates by saying it has to be 11 something. So if you come to me with 18, because you can get any combination, you can come up with combination that'll give you. So Maylene, I'm not looking for the sequence. I'm just looking for that chi-squared value. And Michaela has already given you a hint. The closer you come, it's got to be 11 something. Now, does that make sense? No, okay. Let me clarify, Iman. So the null hypothesis is that there is no statistical difference in the observed and the expected value of the dice. That is the null. So you're not searching for a null hypothesis. You already start with the premise that there is a null hypothesis. Look at Michaela's thing. Then when you calculate uh, the chi-squared value, you look at the chi-squared value in a table like this. And depending upon the number of observations, etc., you say, and again, we're looking for 95%, right? Exactly what he did. You say, okay, well, the chi-squared value that I get is 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 lower than that number, no lower than that cutoff number. So you want to find something that's higher than the cutoff number. But you can come up with any number that's really high and say, well, there you go. But that's not what I want. I want just higher. So you're not searching for the null hypothesis, you're searching for a number that allows you to reject the null hypothesis and show that there is some statistical correlation between your observations as you throw the dice. Okay? So, Maylene, I'm not looking for the sequence. The sequence is something you come up with, and you use that sequence to calculate that chi-squared value. And I'm interested in looking at the chi-squared value. So go look at the video again, see exactly what he does, and then decide that, okay, great. Now I've got to come up with a different combination that gets me to beyond that cutoff. That's up to you. How you calculate is up to you. But I'm trying to say that if you say it's 13 or 16, that yes, that will allow you to reject the null hypothesis. But that does not meet the criterion of just. Just, which means that no combination will give you any lower than that. And whether you want to back calculate it or try different combinations and put the formula in an Excel spreadsheet and then just come up with the one that you got the lowest for various combinations, that is entirely up to you. All I want from the homework is a number. Okay? All right, let's go. Keep going. Now, something you have to identify this thing about a confidence interval. And typically you say that either a 99% or the confidence interval. So what does that mean? It means that, remember the point about inferential statistics, the point of all statistics is we begin to look at a sample. Okay, we begin to look at a sample. And the point of beginning to look at the sample is to be able to then extrapolate to a population. So then you have to ask yourself, what does it confidence interval mean? Confidence interval means that you can basically extrapolate your sample, okay, to the population, and you can do it with a confidence of 95 or 95% or 99%. Now this confidence interval also involves a table based on a certain calculation. So you compute the mean of a sample in order to estimate the mean of the population. Let's look at this a little more. So let's say you have a confidence interval of 95%. Now 95% is that, right? 95% of the sample, 95% of the sample. That's your error bar. So you can see only one is going, two of these is, they are both border, right? So with 95% confidence you can say that your samples are contained in your population. So your confidence interval of 95% becomes smaller as your number becomes bigger. So what does that mean? So let's take a look at this. With a small sample on the left, 95% confidence is similar to the range of the data because it encompasses all the data. But only a tiny fraction of the values in the large sample on the right, that is here, lie within the confidence interval. This makes sense. The 95% confidence interval defines a range of values that you can be 95% certain contains the population mean, right? So if you looked at it, you see this collection of things, assuming that this is very precise data, you'll know that the mean is somewhere here. And if the mean is somewhere here, you'll see that with 95% confidence you can say that the bars associated with the range of the mean lie here. In this case, it's a little different, right? It's a little different because the 95% confidence is calculated for the entire thing. Here, of course, you can also see it's about the confidence. So the full way you say confidence is it's 95% confidence about the mean. Okay, so with large samples, the more precise, remember I use the word precise, which means the larger the collection is, the precision is a measure of the deviation about the mean. So confidence interval is quite narrow when computed from a large sample. Okay, now this is the student's t-test, and I'm going to leave you with this once again. I'm going to basically end the lecture, and I'm going to send you the PowerPoint and everything, and the video. And again, here's another formula for student t. And basically it's a calculation of a variance. And once again, rather than basically belabor you guys with this explanation, we'll go to Bozeman's, and this is the student t distribution. But before I do that, I want to explain something that I normally do when I'm in class but didn't do now. What is this idea? What is this idea of degrees of freedom? What do you mean? What do we mean by degrees of freedom? And always the degrees of freedom is always calculated as n minus 1. So n minus 1 degrees of freedom. Now the degrees of freedom is how many of your observations, how many of your observations are allowed flexibility and how many are not. Okay, so let's say, for example, I have 10 observations and I have a specific I have a I have a specific average value. Okay, now, and there are different ways of explaining, and I'll explain in more than one way just so that kind of it makes a little bit of sense. Let's say I have 5 numbers and the average of all the numbers is 3. Okay, so let's say one of my numbers is 10, another is 12. Now you see, if the average is 3, the other numbers have to be really small, right? But if my average is 3, that means that 4 of those numbers can be anything, right? They can be any number, 1 to a billion, whatever. But one of those numbers, because my average is 3, in order to maintain that average of 3, one of those numbers has to be a certain number, right? One of those numbers has to be a certain number in order for that average to be 3, right? So let's take some other examples. Let's say, for example, I have 4 numbers. Let's keep it simple, right? And the average is 3. Okay, so one of my numbers is 5, the other number is 5, the other number is 5. So my average has to be 3. I have 4 numbers, so I have 15. Okay, 15, and then my other number, so I have to add all the numbers, so that's 15 plus that one number which I don't know, divided by 4 has to be 3. Okay, so it's 5 plus 5 plus 5, so that's 5 plus 5 plus 5 plus x, the number that I don't know, but the average is 3 divided by 4. 3 times 4 is 12. So that x has to be -3, right? The only way the average is 3, and we can calculate this, right? Let's go to the web. Let's go to the web page, and let's open a new page here. And so I can see here that in order for me to have the average of 3, again, I want an average of 3, right? So 5 plus 5, and all these numbers are big, right? Plus some x has to be an average of 3. So I say it, and I'm telling you it has to be -3 divided by 4, which will give me, oops, what did I do? That will give me, let me move that around, that will give me an average of 3. Okay, so let's think about it. Let's say I wanted an average of 3, okay, and my first 3 numbers are 5. Now they could be a billion, a trillion, a gazillion, but the fourth number, if I have to have an average of 3, the fourth number does not have a flexibility. The fourth number has to be adjusted accordingly in order that I get an average of 3. And that's the point of the degrees of freedom. And the degrees of freedom is always n minus 1. In this case, n is 4, right? So only 3 of those numbers can be anything they want. But if my average has to be 3, then the fourth number, has to be able to be, it can only be a specific number if this is going to be 3. Let's take another example. Let's say I have 4 chairs and 4 students, right? The first student who walks in the class can take any one of 4 chairs. So they have freedom. They take a chair. The second student comes in and can get anywhere out of 3 chairs. They take the chair. The third student comes and gets anywhere out of 2 chairs, and they take the chair. Now the fourth student walks in and does not have any flexibility, does not have freedom, and they have to be seated in only the chair that is available. And that's why the degrees of freedom are only available for, out of 4 students, n minus 1. So 3 of them have freedom, 1 does not. That's another way of looking at it. Okay, so we do that n minus 1 degree of freedom, and that's exactly one of the reasons why when we do the standard deviation, calculation of the standard deviation, we calculate n minus 1 because the degrees of freedom and because we're all doing the deviation from the mean, right? And then the one of the term does not have that freedom. Therefore, it's n minus 1. Now you might say, well, shouldn't the population be also the capital N minus 1? Well, not necessarily, because then you have to look at the pragmatism. I mean, it could be, but let's say that you have a sample space of 25 and 24 have a degree of freedom, so you divide it by 24 if your mean has to be a certain number. But let's say you have a population of 300 million, so 300 million minus 1 is not going to change your standard deviation by anything, right? And therefore, in a population, it doesn't matter, basically for pragmatic reasons, because even if you do subtract by 1, it's not going to change your standard deviation by much. Okay, so I'm going to leave you with the formula for this, and then you look at this video, and of course this again, just like the chi-square, you calculate it based on you calculate it based on degrees of freedom. Okay, and I'm sure the Bozeman this Bozeman video will also explain that. Okay, so we'll stop the class now. I'm going to include the link of the video in the chat, so this way, if you have, you can watch the video. If that's the last thing you do before you quit for the day, and I'm going to include it in chat because that was the last topic. And so watch that video. I'm not going to. I mean, I can close the meeting, but you please open the video in the next minute or so before I quit the meeting, and I'll send you this PowerPoint and the video and the link to the video. If not right now, tomorrow. Okay. So final exam 2 o'clock on Friday, next Friday, the Friday after next, and next week will be our last class. Okay, so please open that link, and actually I'm also going to send it to you in your email. Okay, just in case you don't want to watch it right now. All right, guys, I will send the other stuff to you soon. Okay, bye.